really great opportunity to be here in New Zealand. I've gotten to go to Christchurch, Wellington, and meet with them. So I had the opportunity to tour the Red Zone in Christchurch, and I got to meet the city officials, and mind you, devastating tragedy that happened, lives were lost. And talking to the officials there and touring Epic, and I went to Sarah, this is a great opportunity to really create a smart city. So there's a couple things that could happen in Christchurch. One, they rebuild, they add more structural to the buildings, rebuild, but they rebuild the same stock they had before, meaning they don't add any innovation. And I said, boy, this is a great time to pause and really look at how you can add kind of an overlay or use open protocol to make the data available for everyone, not just for the people that run the buildings or property owners, facility managers, and if you think about the broader scheme of transportation. So it was a great opportunity, and I didn't realize that Christchurch is a sister city to Seattle. Something interesting for me. So thank you for coming out. My name is Daryl Smith. I'm the Director of Facilities and Energies for Microsoft Corporate Campus. And I want to talk about the opportunity, looking at this a little differently than I did yesterday. There's over 1 trillion square feet of real estate, and this is commercial industrial, and over $2.8 trillion are spent on energy globally. And this is still the same punchline, that buildings could be wasting 15 to 30% energy, and the people that run the building or manage the building, own the property, have no idea. So this is our campus in Puget Sound. I've told it's over 33 degrees C this week there, so I'm lucky to be here even with a little bit of rain. So they're actually having a heat wave right now. 145 structures, 15 million square feet, 1.4 million meters squared, over 500 acres, disparate building systems, 100 megawatt peak, so we're 3% of the utility grid. Utility grid feeds 1 million people. We can actually move the needle how we start and stop our buildings. $60 million annual utility spend, and we're the third lowest energy cost state per unit in the U.S. There's two other people that got us beat, but it's pretty inexpensive power, and it's mostly hydro. And we're connected to 2 million points, and these points are all the infrastructure, lighting, the air conditioning, power monitoring, and over a 24-hour period, we collect 500 million data transactions. And historically have done nothing with this. So that was our problem statement. Just to recap, this isn't a Microsoft issue, this is an industry issue. The industry, the construction industry, has been building buildings the same way for the last 30, 50 years, everybody in silos. Our vision was to take all this siloed and put it onto one platform. And there are two ways to do it. Either using a rip and replace, where we change all the controllers, all the meters, everything to a common standard. It was $60–70 million. Or we could use software to extract the data out of all the common or all the systems across the campus. And there's two things you need to do with building data: convert it and encapsulate it. Encapsulating it is getting ready for transport. Converting it is changing it from French to English. Well, some of our systems speak Martian, and you have to convert it from Martian to English. And the reason why they speak Martian is when these systems were going in, we had buildings that are up to 40 years old. We have buildings that are 2 years old. When building systems in the construction industry, the OEMs, it was never thought to be an open protocol. Who would ever want the standard? So when we did a multi-vendor pilot, and we did this for about a year, and one of the things we looked for is for the ability to have the vendors pull the data from all the systems. So they had to speak English, they had to speak Martian, they had to speak French. And what we learned is, and this is relevant to, say, Christchurch, if you don't design with an open protocol, expose the data, it makes it a little more difficult. Not impossible, just a little more difficult to get the data. So we're able to aggregate the data from all the systems. We did have some systems that backed it over IP that were already communicating open protocol. But we're also Modbus, Longwords, we were everything. We even have some buildings, just because of the age, that they're token ring. So we've got every make and model and design you can think across our campus. So in looking at our pilot, there were 3 approaches: fault detection, diagnostic, alarm management, and energy management. And fault detection is the ability to see invisible building anomalies. So for an example, well, first a scary thing. When you put a mechanical system, air conditioning, with feeding the cool air in the space, as soon as you install that in any building around the world, it does nothing but degrade from that point on. So that's okay. So how do you have optics? How do you have visual that when it starts running out of design, or the buildings don't run as designed, how do you capture that? So that's fault detection. The other thing is alarm management. So we get hundreds of alarms each day. How do you prioritize that and categorize it and respond to it so you're responding to the things that matter the most? And the third thing is energy management. So being able to see the analytics of your energy consumption in real time. So this is our network architecture. This is a little bit deeper. So if you think about it, you have all your building management systems, control panels. We're so lucky that we have 7 different building management systems across our campus. So that gets aggregated. We have this, what we call the feed store. So this is enterprise warehouse data that is head count, square footage, all that gets fed into our system. We pull in the top right, your left, weather, our maintenance management system, and utility data. So we pull that in, and it's built on, so the back-end SQL Server, Windows Server, Bing Maps, .NET platform. So it really is a Microsoft approach. And we had the bake-off we had. So this is vendors that are building on our platform, not Microsoft creating it. And so this is how we're approaching it for this. And the value for us is the ability to use our own software in our own campus. So that's a good story for us. This is a 300 CFM terminal unit. It's the box that's currently above our head giving the cool air. This is about as small as they come. And this is how they come from the factory with all the metering. So I'm going to walk you through this. So the first ring here is, this is where it gets the air from the air con, from the air system on the roof. You see there's a couple sensors there, and that's what it comes with. It has an actuator. That actuator opens and closes the damper that lets that cold air in. Then you have a thermostat. The system reacts to the thermostat. So if you're hot, it opens up the actuator, brings more cold air in. If you're cold, it shuts the actuator off and turns on the heater. This is the fan that pushes the air through. And this is, we have a resistive heater in a lot of our units, but it could be hot water chilled, but this is where the unit gets a heat. And what happens is that actuator that controls the damper gets stuck all the time, and it gets stuck open. So it's pulling in all this cold air. And then what happens is your thermostat, your room starts to get cold. So the unit says, oh, we need heat. So now it kicks on the heater. So now you have dumping a ton of cold air, and you're heating that air. It's costing you 5 times more energy than you should, and you don't even know it. Because in the thermostat in your room, you're 20, 21 degrees C, so you're comfortable. You're not calling maintenance because you're not bothered. We don't know about it because it's not a, quote, alarm condition. This happens all the time. And we have 20,000 of these terminal units, and this is as small as I get. Some of these units get up to 30,000 CFM. This one's 300. So if you think of it and expand this thing by 30, 50 times, spin around, put some coils in, now you have an air handler, rooftop air handler. Same principles apply here. So it's really, I call it getting our fundamentals right. It sounds interesting that how couldn't you have already known this? Why didn't you have this insight? And this, again, is the challenge with the industry and the industry problem. So everything we're doing, it's not adding any sensors, not adding any hardware. We're using all the equipment, 35,000 pieces of equipment across our campus. We're using the equipment with all the bits and pieces it came with. So thinking about an air handler. So we have 750 rooftop units, and this is one cylinder divide. So you have the outside air come in, you have makeup air, you have your discharge air and return air. So the air circulates through the building. Living in Seattle and living in a climate very similar to here, we like to pull in that fresh air. So use that outside air, pull it into the building, and not run the compressors. Well, what happens for us is the economizers, it gets stuck all the time. So the building management system will say, hey, it's working great, you're pulling that cold air in, But in actuality, we're not. We're running the compressors. And now this is costing me $50,000 a year if I do nothing. So I just wanted to cover some understanding of a fault. So how are we using software to find all these things? And this is the fault detection. So this is that same example I gave you, simultaneous heating and cooling. It's pretty simplistic. It's if the heater's on of the unit and the damper that's putting the cold air in is open more than 40%, and it happens for more than 15 minutes, flag it. Seems pretty straightforward. Would never have the ability to do this before. And I can take these fault rules, so it's just what are the points I need from the unit. This is the syntax, so it's if-then statements that we write. And we actually have a mechanical engineer who's 16, 17 months out of college is actually writing these for us. And then we can monetize them. So then I can tell you how much it's costing. We have a catalog of 195 fault rules. These are our fault rules. So we have everything in there from dampers stuck open, stuck closed. So everything from air handler units, fan coils, terminal units, anything that has moving bits and pieces, we have optics to what it's doing. So we have a catalog, we do this. So then what do we do with that catalog? We drop it in here. So this is actually the solution itself. These are everything we're looking for. So these are all the anomalies when assets aren't running as designed or set points are made outside our standard. So that's what we're combing in there, and that's the fault rule I just showed you. So this one is actually for a leaky chiller valve. And as soon as we connect the building, as soon as we drop this in there, we will continue to scan the campus, this building, the campus, for all the anomalies that we see here. So that's good. How does it look on reporting standpoint? So if you think about buildings, this building is a great example. Buildings are living, breathing entities. So it takes insight from the heat we're giving off right now, and it interacts with it. So from a mechanical standpoint, the valves open and close. Things are going up above our heads all the time just for buildings act as a system. But what we don't know is when is it not working correctly? So we retro-commission or tune a building once every 5 years. So that's when I really look at some of the big systems. But I never do get to the small system because we have 20,000 of them and it's mostly a manual process. Well, now I can look in the building and say, tell me of all the units in the building, much like the ones above our head, tell me all the units that aren't working as designed. They're either stuck open, stuck closed. And then this is what it looks like. So basically what this is saying down here is you're overcooling your building. So you ever been in a building and you're freezing cold and you're just not sure why? Well, it could be, quite frankly, that you have just a few boxes that are out of spec. So one's on the top right up there. You can have just a few broken sensors or misbehaving equipment that is telling that air handler on the roof, that 200-ton unit, we need more air. Dump as much as you can, we're not keeping up. I can actually have one unit in the building, one little terminal unit that can drive a whole air handler strategy, and that is just wasteful. We can look at all sorts of data points. So this is chiller loading. So these points, I could never create this reporting before. It tells us how's the loading doing with chiller. I can look at chiller efficiency. So we have all these abilities to look at our systems. And while I say we're probably one of the largest deployments of a, quote, smart building, intelligent building, there's others in here that are doing it, and there's other proof points. So I work closely with universities, national labs, and here's a couple examples. So Lawrence Berkeley National Lab, they have a really great scientist crew out there. They've done research on where this low-hanging fruit is. Texas A&M and Pacific Northwest Labs. And they're proving in their research with hundreds and hundreds of buildings the same thing that we already knew. There's a lot of opportunity out there. And the way to get to it is through software. So we keep saying, or I keep saying, I sit in a financial organization. A lot of what we do is anchored in cost, which is our return on investment. And we really have that as an anchor for how we approach work. Well, it's not always about the cost. So this is the second floor of one of our buildings. You don't want to see water coming out of the second floor of one of your buildings. This is what it looks like inside the building when the water is coming inside. So a chilled water pipe broke, and all the building water that was up above the building became in the building. And one of the challenges here is it's not always about the cost, because if I have optics to how equipment's starting to run as designed, if things are starting to occur in there, it really does drive business continuity. We have labs in our campus. Our labs, I think we have 470 across the campus, and they consume 47% of our energy. So they're software, mini data centers, and they work on everything from the Windows 8.1 release to new products. And if labs go down, I have a really bad day. So while the energy is really important, business continuity and reliability is more. So having the ability to tell when the campus, to precursor of a catastrophic event, is critical to me. So I could spin this whole conversation and say, yes, it's cost, yes, it pays for itself, but something just as important is the use of software for uptime. So I want to talk a little bit about how we did it, and then tell you about some of the other cool stuff we're working on. So we had 4 principles when we go about anything. It has to be beneficial, practical, scalable, and supported. So beneficial, it has to have a core reason to do it. Practical, I could put IP-enabled lights across the whole campus, but does that, is that really that important at this time? Is there an ROI? Scalable means I have to be able to take it across 15 million square feet. And supported, so the minute I touch something and it doesn't work, who do I call? These are our requirements I wrote. We created 195 requirements of everything we wanted to do when we grew up, what reporting do we stop doing, what new reporting do we have. It was everything we wanted to do. This is the solution scope document. So this really broke in and characterized everything we had. So we knew we wanted to do alarm management. So it really took that what's in scope, what's out of scope, because you really have to define the problem statement. From there, we had use case context diagram. Now, on the legend here, the people, we call them actors, who was going to interact with the tool, in the facilities world, we never use the word actor, so I'm assuming this is an IT word. But nonetheless, we really looked at what were the data sets we had available, who was going to interact with it, and this is partial to the stick diagram. And it gives us insight to really mapping out what we want the solution to do. So this is kind of the rigor we went through on top of talking to about everybody I could of what was out there in industry. So with that, we have the Redmond Operations Center. So today, we manage 1.4 million meters squared of space, plus our California campus, so campus 300-400 miles away. We do this all out of this building here. With the ability to do the fault detection and optimize the labor, what this is going to evolve to is the Global Optimization Center. So we're actually going to run the analytics and faults for all of the buildings we deploy the software in, and this is where the magic's going to happen. And that's one way of doing it. And we have a staff, and I have talented people, and they have these capabilities. There's vendors that provide this as a service. So some companies say, well, that's great, Daryl, you have a nice ops center. We don't. What do we do? Well, the other option here is even a software as a service play. So use the cloud, port the data up, and have it consumed there, and let them provide the engineering for you. In fact, on the broader term, so we're in the private cloud now. We're actually going to move the whole building management system to the cloud as well, because my IT costs go down tremendously on that. But the value here is data. So whether it's building data, use data, security data, it all can reside up there, and then whoever needs to consume it can consume it. Also, I want an end-to-end process. So I want a work order to come in through our work order system. So if you're working at Microsoft, this is the front end to our work order system. Or I want to come in from our smart building solution. It flows into our CMMS. And our CMMS is our computerized maintenance management system. So it's where our work order system, it's the back end of where all the work goes. And then from there, I want to flow it where I need to for capital planning, design, occupancy. One of our campuses, we over-designed it by $8 to $10 million because we didn't have the data of the employees that were going into it. So we had a certain design per developer, and we designed to that to 600 watts in office. The group that was going into this campus were running a lot hotter than that. So we upped the design standard. Well, we're operating at less than 400 watts an office now. So not that I only over-designed it by our standard, I just over-designed it by what we designed it to. So a lot of waste there. And one of the challenges is, when we're designing buildings, we look at weather, we look at what the space that people are in, we check the wind temperature, and we design. If you have rich information of how people are working the building that's trending over a period of time, we would have been a lot more precise on our design. So this is our roadmap here. We did a 12-month pilot or bake-off that ended in 2011. We're deploying the solution. We'll complete this month. We're going to integrate an end-to-end process with some of the other systems and looking at smart grid readiness. Smart grid readiness is interesting because it's looking at how do you recover from what is a 2-hour power outage to a 2-minute. It's working with the utility. And future to that, it's how do you use your building as a battery. So utilities are keen on this. This is important for us. And I want to talk to you a little bit about app development because I think this is pretty interesting. All right, so I have my cell phone, and we either have near-field communication or the tags program, and I'm not sure you're familiar with that, but near-field, you put your phone on it. So if you think of it this way, when Daryl goes out to do work orders, or Daryl's team, we do everything on paper. We have a clipboard, so we have the work orders. Here's your work orders, go to your work orders, go out in the field, do it, and that's ridiculous. And the way that people work is maintenance people go in and out the building the same way, so they typically don't look to see, well, why I'm in the building, what else is broken? Well, how could you? So we're using mobility in rugged tablets and our phones. We're working with one of our partners. I want to just show you some screenshots on my phone I took yesterday. So this is a phone, and it recognizes what your location is through GPS. So I'm in Redwood C, and I'm walking there to do my task. But on the phone, I can say, boy, I have issues, and I have some other things flagging up here. So I have other opportunities to do stuff while I'm in this building. So I look at it, and I said, wow, there's things in this building that are broken, that are outside what I was going to do, but this is something that's wasting energy, and I have the ability to look into it. So I can look down, and I can say, okay, it's that little unit in Daryl's lab. What's wrong with it? What are the causes? What are the fixes? And by the way, we have tags on all the equipment. So not only can I tell how much it's wasting, how to fix it, where the probable causes are, I can know which equipment I'm at. So before, I had no idea on productivity. So when somebody starts their maintenance, they do it. I'm on air handler number 4. I did my maintenance. I'm going to the next unit. Well, Daryl didn't know he was on air handler number 2. He wasn't even on the right unit. So we have tags on all our systems to allow, I tag at the unit, I'm starting my maintenance. Then I'm completing my maintenance. And Hillary, she can do it in 30 minutes. Daryl takes 2 hours. Well, is Daryl doing too much? Is Hillary not doing enough? To be able to understand all the analytics of how we use labor, it's interesting what you find out. But say if I'm at the unit and I just can't remember how to start and stop it. So I go to the screen, I'm on this unit, I click on it, and I click it's a nailer. Then all the maintenance procedures, the start, stop, are all on my tablet. So I don't have to worry about going back to the shop, getting the manual. It's everything there. So you can think of it as you have your own design shop, your whole maintenance, your own manuals right on your phone. And this is a game changer for us, and this is driving a lot of productivity. What we're doing too is this is an Azure-based solution, so we're actually doing it in the cloud. So I can actually turn off the unit in my lab from right here. So I can actually control it. And we're not using the BMS, I'm actually going right to the machine itself. So think about the value to that to me. If someone says, okay, as long as you can keep our buildings between this temperature and this temperature, I don't care how you do it, we can actually do command and control, we can do sequencing that is the most efficient. So as long as I stay within that temperature range, everyone's happy, but we can do different sequencing and different control strategies that will actually drive energy costs down. We can do it through the cloud. Microsoft is a pretty large campus, and we have agreements with the city that we have to move the people in and out of work. We have to lower our SOV rate, which is our single occupancy vehicle. So how we do that is we have a fleet of buses, a fleet of shuttles, So we have 22 connector routes, is where we take people back and forth to their home. 69 buses, 6,000 seats. We have 135 shuttles that do 7,000 trips a day. Now, a trip is picking up one person, picking up the second person, and taking to their location. And for a campus that houses 58,000 people, that's a lot of movement. So we want to encourage people to use it. And we have Priuses, we have Leafs, and so it's a good story. Well, we have a campus experience app. So this is an app, some screenshots I took yesterday. And in this app, I can order a shuttle, I can book a room or find out what room's close to me. I can find out what's happening in the cafes, what are they serving in the lunch, all from my app. So, in fact, yesterday I ordered a shuttle from New Zealand. Now, when it gets here, I'll be really surprised, but but I actually ordered it from building 21 to building 4. So from 21 to 4, it tells me, well, it's shuttle number 792. That's who's coming to get you. And I can follow that shuttle on my phone till it gets to me. So we have SLAs on the campus. It has to be with you within, I think, 5 or 7 minutes, and it has to get you to your destination in 15 minutes. But I can actually track it with my phone. Same concept in our bus system. You can book a seat in the bus. It'll take you home. You can see where the bus routes are. That's the ability of mobility is changing how we're our productivity in the campus. If you didn't see it yesterday, I really like this example. We have 8,500 fire extinguishers. We spend tens of thousands of dollars every year with somebody walking around with a punch card. Why? So what we had done is we put the fire extinguishers on the network. So this is working with a partner to have a tether that checks when the sensor, if the pressure drops, checks if the cylinder is removed or if cylinders are blocked. If any of those conditions occur, it sends a note to security. So we've ran it for a year and a half, have yet to have a false positive. So anytime we have had an alarm, it's because somebody has removed the fire alarm or fire extinguisher or blocked it. So it's been a very effective way. The fire department has bought off on it because we can provide a ton of reporting. So again, it's data is king. And so we have that capability. So it's interesting that everything we're doing in our campus, I would call getting our basics right. We're not doing anything that's reinventing the wheel. We're just really solving basic problems that exist. And we've been fortunate enough to be recognized in Computer World's On-Air program. We were a finalist for a laureate. Cornet Global is a global premier real estate company, and Realcomm is it's really where IT and real estate collide. And we were recognized there. And one of my jobs and why I'm here today is to continue to advocate it. So my charter, on top of running a very large campus, is to get the word out that this is here and now. And my hope is that my story becomes diluted because everybody else is doing that. That's what the hope is. So I want to recap. So it's 125 buildings, 2 million data collections, 500 million data collections every 24 hours. We take different protocols, we take different hardware and interfaces, and we collect that data. And we make information actionable, and we make data actionable information. We maintain over 30,000 pieces of equipment. And what's interesting is 48% of the faults or anomalies we can correct in 60 seconds or less. 52% other, we have to roll trucks. And then we're targeting 6 to 10 savings once we have this all rolled out. And I think I'm being very conservative because I sit in finance. As far as what I'm telling my boss, it's that. But I think we'll do better than that. And then we have over 32,000 work orders. So it's not just finding everything that's broken. It's really about how do you prioritize what's broken in your campus. And it makes sense not only for Microsoft, who has a medium-sized city, it makes sense for cities. So City of Seattle is taking what we have done and they're doing it themselves. So they have disparate building owners, different companies. So they have universities, cancer research, hospitals, and government buildings. And they are connecting all these buildings through the cloud and taking all the data to a common platform with the intent of sharing this data amongst all the companies so they can help drive down the energy. And every building's jumping off point's a little different. Some people have more metering than others, but there's solutions to meet what you need, what you're trying to achieve. So I think that's fabulous that in a city, you have different companies that have no other connection to each other except a common goal to reduce energy, and I think that's fantastic. So I'm going to give a shot here of trying to do a live demo, and let's see how we do. Everybody cross your fingers. I'm hitting the server 8,000 miles away. Ah, wonderful. It looks really great, or let me just tell you. Let me see, it may not be coming up like I thought. Ah, it is. How do I toggle the screen? Oh, because I can be doing it. All right, so. Yeah, I know. It's sad to say when we were in our first meeting, we had some of the brightest people from universities that we were discussing. We couldn't get the projector to work. So we called IT and said, this is ridiculous. We can't get the projector to work. The person walks up, stood at the table, turned it on and off, and there you go, guys. So needless to say, I surround myself with smarter people than I. Ah, can you see it? Great. Thank you. Sorry, thank you very much. So this is our campus. This is live data right now from our campus. And what you're seeing here is what are the top left, what are the top performing buildings in our campus? Who's winning the race today? Building 1's winning the race. And it's a BPR, Building Performance Indicator. And it's a PUE calculation. It's total load divided by plug load plus lab load. We're at 65 megawatts. And I shouldn't have done that. If the blue is weather, the red is energy consumption. You can see it's been in the 90s, over 90, so over 33 degrees Celsius, so it is a cooker right now. We're at 65 megawatts, or almost 66 megawatts demand. This pie chart, it would take me 8 weeks every year to tell our executives where the energy went. Now it's being updated in real time, so I can ship this to Excel. So let's see, how did we do the campus this week? So I've been here at TechFest having a lovely time and being hosted from some really terrific people. So I can come in and say, okay, so how did the campus do this week? I can zoom in and say, okay, how are we loading it? Meaning, how are we starting and stopping our buildings? What's it look like? Are we having any major movements of equipment? So I have great optics on that. Go back in time, go back as long as I want. I can ship this to Excel. The load segmentation, so base loads, core and shell, common areas, how long we run the buildings, plug loads people, and labs is the power for the labs. That's how we think of our energy strategy. So I can go into each of these segmentations and I can tell you what they're doing. So I go into plug load. In about 7 seconds, I'm guessing from here, this is what people are doing it. This is what people are driving. So let's see what time folks came to work today. The value to me, so you see the loading, it starts at 7:25, 8, and some at the crack of 9. But I can see loading, I can see when we're taking lunch. What the value is for me is we can apply tactics across the campus, and I can say, yes, that works, or not so much. So I can do that in the base load, plug load, and lab load. I can also go into every building in our campus, and I'll pick, let's pick buildings 32 through 5. Yeah, let's pick 36. 36 is one of the buildings that we found a considerable amount of energy savings, and it was a LEED building. It's very, very well designed. But this just goes to show that if a building's not operated in a sustainable way or in an energy efficient way, it's not energy efficient. So we can see the 3 boxes to the left here, type of building, type of system, square footage. How many people are in the building? What's the demand? So we're at 2.2 megawatts, and how's this building performing, and how did it perform the last week? So the same thing, I can go in, out, and have a lot of optics into this that I never had. So this is really about managing your energy and having that capability. We're tied into the HR system. So we haven't tied into the badge system yet to say how many people are in the building right now. Get that one started. And a value for this is In some of our buildings, we were finding that we were starting the building systems the same time the labs were starting, the same time that other things were going on, and we were causing a 3 or 4 megawatt spike in some of our large buildings. Well, I pay $3 to $5 a kW per demand charge, meaning utility, and this is consistent around the world, the utility looks, what is your peak load for the month, and you have a charge against that. So if I can put control strategies in play, well, one, you shouldn't be causing that problem yourself, so stop it. And further that, if I can start to see when I'm coming to that peak, and I put control strategies in, I get to smooth out that curve, that's money to us. Also, we start and stop our buildings every day based on a timer. So we should start about 6 or 7, we shut down about 7 or 8. Well, why? Why aren't you loading when people are in the building? Why aren't you looking at other data points to say, how do you run that? So this is one of my other dashboards if it loads. This is our Redmond, give it a couple more seconds there. Lovely. Talk amongst yourself for a second here. So this is having optics that goes deeper and deeper into the building. So energy management allows you to have the ability to look at your consumption, to look at what you're doing, to have your impact. So this is East Campus, all these little dots here. And in East Campus, across the campus, if we had a power anomaly, we roll a truck. And everybody grab a building, including myself, start with the most important buildings, work your way down. If you can see on there, each buildings have these smart pins on it. So I can look across the campus, scan, pan, in about 90 seconds to see after a windstorm or power anomaly or any type of event, does the building have utility status? Are the backup generators running? Do you have communications? Are there faults and alarms? Get the whole campus in about 60 to 90 seconds. Took me 4 hours before. So that's a pretty good efficiency factor. And then we can dive into, let's go to West Campus. Studio C. So I can dive into a building and say it has the same static and dynamic information it does before, but it has those numbers. Those numbers are in red because red is bad. I can go to each floor and tell you how something is running on the floor. So any of the assets, and these are the terminal units, these are the same units that are sitting above our heads. Any of the assets that aren't working as designed turn red. I can click on the asset and say, why are you red? And more than likely, this would be conditions that we would never have seen normally. And these are conditions of the equipment not running as designed, or somebody made a set point. So at 12:16 a.m., this unit came on. So that's a little after midnight. It's costing me $169 a year. This is the same example I did on Sunday. So I have something wrong with this unit that's coming on in after hours, and it shouldn't. It's like you go by a building and you see all the lights on, going, well, that's interesting. I wonder why all the lights are on. Things come on, schedules get corrupted in the system. It's having optics. So I can look at it from a building level. And I have a couple other views that I like here. So let's look at current faults. So we prioritize our faults. Go back to Studio C. We prioritize our faults by 1 through 5. Priority 1 is the most complex or most critical areas, and we should never have something there that if I'm not running. Priority 5 is my office. So tell me everything in priority 5 where systems aren't running as designed or there's a set point not made. So these are low impact to the business, but again, issues. Priority 2s are labs. We better be correcting these, because this could lead to that water deluging the building. This could lead to potential lab outages. This is the precursor to a catastrophic event that we wouldn't have had before. And I can look at it at a building level. Let's look at it as a campus level. Let's see how many areas or let's see how many opportunities we have right this very second in Redmond. So I've just casted the net across the campus, and I'm telling the system, tell me of all our assets, what's not working as designed, and where do I have set point changes that we need to fix. There may be a couple, so it might take a second here. Yeah, there's a few. So So this is great because it allows us to prioritize the work. So I would say the spigot that we have is open 25%. I'm not telling the system to go find everything that's broken. We're going after the things that matter the most, the ones that have business impact or wasting a lot of energy. Over time, I'll continue to open that spigot and more, and then get to the entire campus. So I have in West Campus 309 pages of opportunity. Remote campus, this is all. Remote and East Campus, 75. So East Campus is doing pretty well in comparison. So I can take all these faults and I can fault them by type. So I just drag this guy here, boom. These are all the things I'm looking for. These are all the faults that are wasting money. I can explode it now by all the fault types. So tell me all the leaking chiller valves around the campus. And this tells me how much energy we're wasting, where those anomalies are. And I have a couple going on right now. So it's having these capabilities that we didn't before. I think this is fantastic, but I would say the reporting capabilities are even better than everything you've seen, because it allows us to automate reporting that would take us hours and hours and hours, to the point that we stopped doing it because it wasn't cost effective, it wasn't labor effective. So on the reporting, and how am I doing on time? 5, thank you. These are all the different types of reporting we have. So I can look at building performance, fault reports, mechanical reports. It's reports I could never have done before because it was too costly in a labor standpoint, or I just, quite frankly, all the different systems, I couldn't get the data out of them to even create these reports. And I can click on, let's see, building unit, that's a good one. So I can run it and it looks at over time. So let's see, AHU5, let me grab one. And this will take a couple minutes to run here. So what it does is it takes what would have taken me 4 to 6 hours into a matter of a minute. And it gives me information on how is a unit performing over time. And this is valuable for us. So typically it's about 80,000 lines of data flipped over to a graph charts. It creates the charts and stuff for us automatically. So it's not even the point where we have to take it and take the data and create the charts ourselves. It automates it. So we're big on automating all sorts of processes we have. Well, instead of waiting for that, I just want to see if there are just a couple questions now. Yes, sir. Yeah. Absolutely. Yeah. It's built into not the logic of the reporting, but it's built into other reporting we do. So as our capital planning, that's a great point, is we have $4 billion of assets in our campus, and our finance team doesn't like what I give them for our capital planning. I tell them age of equipment, run hours, we try to find some our maintenance records, we kick the tires. And that's really how we do our capital planning, and it's just not that deep on detail. So for them, they want that rich data. So I can look at how's it doing, and we have the maintenance work orders at time. That's why I want that end-to-end process, where the maintenance and CMMS is all aligned in there. Is there any other questions? Yes, sir. So for us, there's some faults we don't fix. We just add to the next maintenance cycle. Oh, this is lovely. So here's example, raw data. It's probably 80,000 lines of data. It tips it to a pivot chart. And what this is telling me, and this report would take me 4 to 6 hours. So this one here, that center chart, get a little zoomed in here. The center chart is my economizer. That allows us to pull cold air in, or free cooling. And so it's valve position over temperature. So what I want it to do, it should hang around 10% until it gets into a certain area, open fully, run, and then when it gets hot, close. Well, what this sucker's doing, it's opening when it's 52 degrees, and it stays open, and it closes in the 70s. But this is anomalies that we can see in the system. If you know what a duct static strategy is, we don't, because it shouldn't be a flat line. The red is weekday, the blue is weekend. This shouldn't be running. This isn't a lab building, so it shouldn't be running on weekends. And a mechanical engineer can look at this, and these are all the the mixed air. So this is one unit, one air handler for a period of time. I have 750 air handlers. I'll never get to the campus at that rate. I sure can at this rate. So your mechanical engineer can look at our makeup air, discharge air, all the points on there and say, yeah, you have problems, or this one's great, go to the next. So this reporting is the report that I'm most excited about is the one we're going to create next. It just gives it, if you can dream it, you can create it. And that's how even this one came to be. So thank you for coming out. I appreciate your time and hope it was valuable.